Good. Okay, live there. All right. You guys are awfully quiet today. Let's take a vote then. How many think with the salt water and the regular water ice cube, the water level is going to go down? Okay, how many think there's going to be no change? How many think it's going to go up? How many don't think? All righty. Well, let me share the screen here really fast. Okay. Online, hopefully you can see the document camera now. All right. Let's quickly run through this concept. So here we go. There's our cup. This time it's going to be full of seawater. And here's our ice right there. Down here is seawater. So we've come to the conclusion or the agreement, right, that based on the principle of buoyancy, that if this is regular water, when we take the sum of the forces in the y direction equal to 0, we get the buoyancy force right here, and we get the weight of the ice pushing down. So if it's just regular H2O, we get then the buoyancy force minus the weight is equal to 0. And we know that the buoyancy force is gamma of water times then the displaced volume minus the weight. And the weight's going to be then the volume of the water, not the displaced water, but the volume of the water times gamma of water, right? Comfortable with that? And we said if it's regular water, I think I use this analogy, if somehow I had a magic lightsaber where I was able to go in and carve out a block of water while it's still liquid, I would know that the force acting on that block is equivalent to the buoyancy force, and the weight of that block is equal to that mass of water above there, right? Those two have to balance each other out. Otherwise, the water wouldn't be in static equilibrium. So again, if I'm able to cut out a block of water while it's still liquid, the forces on the sides and the forces on the bottom all have to be equivalent for it to be in static equilibrium, which means the weight of the block and the buoyancy force have to be equivalent. Correct? Okay. So making that as a true statement, if now we come in and say, all right, we're going to replace the water in here with seawater. So now it's gamma of seawater times the displaced volume minus the volume of water times gamma of regular water equals 0. Okay. We haven't changed this. That's still the same. Same block of ice, same size, same density, same specific weight of water. But we have changed the gamma of the seawater, right? Okay. So if we've displaced the gamma of seawater, what does that mean about the displaced volume? If one goes up, the other one. Go ahead.
It should have decreased. I was just going to say it should have decreased. Where the gamma went up, the displaced volume should decrease.
Correct. Yeah. The displaced volume has to decrease. And that makes sense. Now we have a heavier fluid holding that block up. So the ice is the ice, before it melts, is the ice going to ride higher in the water or lower in the water than if it was regular water? It's going to be higher. Yeah, it's going to be higher. So if the block is higher, because we had to displace less, and yet we still have the same volume in that ice cube, when it melts, what's it going to do? It's going to raise the water level, right? Because that extra water has to go somewhere. And we just kind of showed it there with the equation. So you guys need to write that up in some way using words or equations, right? Part two of this not of the homework problem, but of the thought question, if you will. Because I had a student several years ago that went and did this. He said, you know, I was at a restaurant and they brought me my big tall glass of water, chock full of ice. You know, restaurants, they fill it up full of ice. He said, I had a little marker there, so non-permanent, as I marked on the glass, and then just didn't pay attention to it. And then we were there for a long time, and it pretty much had all melted by the time I got around to looking at it. So I had another drink there, and so, and it went down. Back to the original statement, water on water, we said it didn't change, but he said it went down. Who's telling the truth? Or what's happened here?
Well, didn't some evaporate, maybe?
Evaporation is real, and if we were physicists, we would look at evaporation, but it's not going to evaporate that fast over the course of maybe 30 minutes to really make a huge difference. There was something else going on.
The ice cubes on the bottom of the glass are all the way submerged.
So we changed the parameters. We changed the constraints of the problem. Now, rather than it being one floating cube, it's a glass that is full of ice, and that ice is up against the sides of the wall, and the ones on the bottom. Was that you, Scott, I think, or Nico? Was that Nico? I wasn't paying attention. Whoever it was, thank you. They're all submerged. So because ice has a bigger volume, they are taking up more space than they need when they melt. And so when they melt, water level went down. So we didn't, neither one of us was lying. It's just that the problem changed. And you know, that's a significant thing. There's a reason why I bring that up, because as we talked about momentum last time, I told you about when I made a mistake, when the problem was changed and I didn't recalculate it. We have to understand all the components, all the variables, all the constraints when we're trying to do a design. Otherwise, we're going to miss something and get it wrong. Okay? All right. So one final thing from chapter 3 that I want to cover. We're moving on to chapter 4. While I'm thinking about it, I kind of rearranged things a little bit differently this semester. So I thought it would feel a little better. And on the homework that I gave you, you'll notice that inside the text, I changed it to give you the pressure at all 3 exits of that T, if you've taken a look at the homework, right? And after we cover some stuff today, you wouldn't need the pressure at all 3. You'd only need the pressure at 1. At 2 of them, and you can find the third one using the energy principle. But since we haven't covered that yet, I just gave that to you, and then you can go ahead and solve that problem. And I'm wondering if I took that out of my notes and forgot to stick it back in here. So I'm not seeing that principle I want to cover. All right. Okay. Let's talk for a minute. Okay. So if we have the random control volume in space. So what we're going to talk about today is correction coefficients. I mentioned this at the end of class on Friday. Okay, so we have some control volume out here in space. And we know that fluid is moving in and out of that control volume. And there is some specific volume going in, or velocity, sorry, some velocity going in and velocity going out. We could have multiple streams of velocities going in and velocities going out. And we know from continuity principle, if we take the velocity and multiply it by the area, we get the flow rate, all right? But the basic question for you here, if I take a set of numbers and if I add them, if I have two columns of numbers, and if I add those columns up and then I square the addition and multiply that addition by the other column that's been summed and squared, and then take the square root of that, is that the same answer as if I take the individual rows, A times B, and then C times D, or say X1 times Y1, X2 times Y2, and then if I sum all those up and take the square root, does that give me the same answer? So for example, if I said 1, 2, and 3, and I was going to multiply. Sometimes it works out though, so I got to be careful here. So if I took 1, 2, 3 and added them up, I'd get 6, right? 6 times 6, 36. And of course, the other side's 1, 2, 3 as well. It's a pair, so 36 squared is 6. It doesn't matter. But if I take 1 times 1, 1, 2 times 2, which is 4, so 1 plus 5, 1 plus 4 is 5, and then 3 times 3 is 9. So 9 plus 5 is 14, and the square root of 14 is not 6, right? So they're not equal. There's a simple example there, we're not equal. Well, when we put the velocity, when we square the velocity, like you've seen momentum, the velocity was squared. When we square that velocity, then we get a different answer. So if I have a velocity coming into that control volume that is not uniform, that is not the same velocity, then my energy calculation is incorrect. Does that make sense? So for example, now if I take my control volume over, say example, a pipe. So now we're going to go to something that is a little more of a controlled control volume. It's a fixed control volume. That's a better way of saying it. It's a fixed control volume. Okay. So flow is going in, and I've got a control volume there with the hash marks. All right. And in real life, the velocity going into a pipe or along a pipe is not a flat velocity distribution. In fact, if I take this here and blow it up, okay, so what we have as far as velocities, this would be what we call the ideal case. The velocities are the same. It's the sum velocity. The next thing we have is the laminar distribution. And laminar, if you remember back to fluids, how do we know if the fluid is turbulent or laminar? What's the guidepost that we use? So the Reynolds number, here's where I want to make a little bit of a distinction. You're absolutely correct. You've identified the correct non-dimensional parameter, the Reynolds number. The Reynolds number is a guidepost. So if we're talking about pipe flow, depends on who you ask, but anywhere from 2,000, 4,000, somewhere in there. They say anything less than that is laminar, okay? Anything bigger than 10,000 is turbulent. And in between is this transitional range that we don't know. So we don't know if it's 2 to 10 or if it's 2 or 4 to 10 or 4 to 12. In fact, you can actually create laminar flow at higher Reynolds numbers if you're really, really careful and if you know that. But that's not the point. The point is it's used as this distinguishing point. And if you get in groundwater, it's usually 1 or 10. Reynolds number of 10. Anything higher than 10 is turbulent. Your open channel flow, 500. So that value changes depending upon the fluid and the situation, but nonetheless, it provides them this separation if the flow behaves laminarly or if it behaves like a turbulent distribution. So laminar, we get this bullet-shaped velocity profile, if you will. And turbulent, where it's mixing a lot, it's relatively flat, but it does go down. We have shear stress at the side of the pipe due to the non-stick or the no-stick principle, which means that a fluid next to a solid surface moves with the velocity of the solid surface. So if the pipe wall is not moving, there is the first molecule of fluid. It's attached to that solid surface. It doesn't move. Now, does it move not all the time? Well, no, I'm sure another fluid particle could come along and bump it and make it move. But the concept is that there's no velocity on a solid surface that's not moving. And if the solid surface is moving, then the velocity next to the solid surface is moving at the same velocity. Okay? So both of them start here at 0 and go out where the ideal one, automatically you have that velocity. All right? So what I'm trying to point out here, even in a pipeline, if we have turbulent flow, it's still, if we measure the momentum transfer near the boundary, it's not equal to the same as the momentum transfer in the middle. And we have to take that into account. Now, we could go into some big derivation, but I really don't want to do that. I just want to kind of stick with the basics here. And we could say then that the momentum correction coefficient okay, it tells us that, take a step back. If we know kind of the average flow, then we can find a correction coefficient okay, once again, let me take a step back before I say this. In this course, and what you do out in practice, when you're out in the field, you're going to treat the flow as one-dimensional flow because it's easy and it works. So this concept here of an ideal flow works for most of what we do. There are some exceptions to that, but like I say, 99% of what you do, this is going to work great. So we want to tie in how do we account for this if we're going to use this method here. And so we're going to use average values to figure out what this correction coefficient is. So the momentum is a function of v squared, right? V squared, we've looked at rho. Momentum, the momentum function, when we did that on the right-hand side of the equation was rho VQ, but Q is a function of velocity, right? So let me write that on here. So just go back and look at the momentum equation. We said the sum of the forces is equal to rho Q V out minus rho Q V in, right? So V is that's velocity, and then Q is a function of velocity. So momentum is really a function of velocity squared. So we just have to make an account for how do we adjust for this velocity being squared when we're trying to calculate momentum, okay? And quite simply then, the momentum correction factor, beta, is equal to the integral of v squared integrated over the area. There's the account. This is where we're taking into account that it's non-uniform, divided by then the average area, I'm sorry, not the average area, but the total area times then the average velocity squared. So V bar represents the average velocity. That's the ideal flow. So up here in ideal, I'm going to put V bar up there. That's ideal. So I'll make the note there, V bar is ideal. So my equation beta is equal to the integral of V squared integrated over the area divided by the area times the average velocity squared. And hopefully that makes sense to you. When I integrate across the area, I get the area. And if I'm using the average, if the velocity doesn't change, if I have a fixed velocity, then I can just go ahead and square it. And then this is going to give me the correction factor. Okay? So in other words, if I took and multiplied this the other way, I could say then that beta times the area times velocity average squared is equal to the integral of velocity squared dA. And that would account for the momentum correction factor. So anytime I'm using momentum, technically if I wanted to do accurately this equation, I would come up here and put my beta right there and put a beta right there, and it would work. Then I'd know perfectly. But I have to know what beta is, right? Now, typical beta factors range from 1 to 1.3. So beta is less than or equal to 1, I'm sorry, less than or equal to 1.3 down to 1, somewhere in that range. And actually, I think 1.3 is really high. Normally, it's like 1.05. It's pretty small. Let me just look in the book here, see if they... Okay, 1.03 to 1.06, so that's probably a little high. Let's go 1.06 on that. Okay, so it's not that big of a deal. Really, you know, if we're that close on momentum, we're like, that's good, life is good. For the energy correction factor, and we haven't really talked about energy yet, that's where we're going to go. But for the energy correction factor, it's a function of the velocity cubed. Because kinetic energy for a solid, v squared divided by 2, right? That's kinetic energy. But with fluids, remember, we're transporting. So momentum, mass times velocity. Well, it turns out here to be velocity squared. Kinetic energy, v squared divided by 2. But in a fluid, because we're transporting it, we have the flow rate q, so now it turns out to be velocity cubed. So our kinetic energy is a function of velocity cubed. So if we do the same thing for the velocity correction factor, we get then that alpha is equal to the integral of v cubed, v cubed integrated across the area, divided by then the area times the average velocity cubed. Okay. Now the range for alpha is much bigger. So alpha can range from 1 to as high as 2. And it depends on if it's pipe flow or if it's open channel flow. In pipe flow for laminar flow, the kinetic energy correction factor actually tends towards 2. So if you're doing research work on laminar flow and you're not doing the integral, then you may want to include a momentum and especially a velocity correction factor to So why do I bring this up in this course? Well, for most of what you do in practice, you're not going to worry about this, except there's one scenario where it's different. Now, if you go into research, where you're really trying to figure out the process that's going on, you want to know your inputs, you want to know your outputs, then you're going to be worried about the correction factors. But most of what we do is turbulent flow. So once again, if you're doing laminar, that's different. But most of what we do as civil engineers is turbulent flow. And turbulent flow, alpha and beta are close enough to 1 that we normally assume that they're 1. With the exception for open channel flow, okay. In open channel flow, this concept is applied a little differently. How many here, I'm looking at those online as well, how many here have heard of HEC-RAS? One, I know there's a couple that have in the other class. Okay, HEC-RAS, Hydraulic Engineering Center, that's UC Davis. There's a whole bunch of different HECs, HEC-RAS, HEC, HMS, HEC 2.0, HEC 10, a whole bunch of different HECs. So they come from the Army Corps of Engineers, who has kind of an academic post, I think, down there, and the RAS, R-A-S, so HEC, H-E-C, dash RAS, R-A-S, River Analysis System. HEC-RAS is the most widely used software for doing open channel river type flows, for flooding and so forth, because I think it's because it's free. Now there have been companies that have come along and put nice front ends and nice back ends on it, charge, but it's a very powerful tool that's used quite a bit. But when you have an open channel system, such as a river that's flooding, most of you have taken the engineering hydrology, right? So if we have open channel flow compound system, or a compound.
For some reason it's not showing up on
It sure isn't, isn't it? Okay. That is just weird. All right. Try this again here. There we go.
Now it looks like the words are.
There we go. Okay. And bring it back. Let's share screen again for those online. Okay. Those online, can you see that now too? Your thumbs up or something? Okay, thank you, Scott. All right. So, so we're looking at open channel flow, a compound channel. So what does a compound channel look like? Well, a compound channel then would be something on the order like this. Okay, and here's our water level right here. And this is the main river. So the main river, when it's not flooding, the channel is within the river. All right, hasn't spilled out, it's not overbank. Once the water spills out of the overbank, what we call bankful discharge, once it spills out into its floodplain, the floodplain has a different friction factor than the main channel. Think about a typical river, rocks, boulders, maybe a few shrubs on the side, but that's no big deal compared to most of the river. But once it floods out of the main channel, then you're talking trees, brush, buildings, you know, it could be all sorts of stuff. And so the roughness over here, we'll put some grass and some shrubbery there. Once again, it's hard to imagine that I didn't go to art school. You know? And then over here, we're going to put some trees. Okay, so there's going to be different roughness for those components. So when we go ahead and calculate the momentum going down the channel, we have to treat these as different parts of the channel because the velocity is significantly different in the side and than it is in the side, than it is in the middle. So we're going to go ahead then and split this into our 3 parts. And we will call this then part number 1, part number 2, and part number 3. And so when we do our calculations for this, then we have to note that beta is equal to the sum of the velocity squared times the individual areas divided then by the total area times then the velocity average squared. And I'm going to put a sub I and v sub I right there, where I is equal to 1 up to n. Didn't leave much room there, but hopefully you can see that. So beta is equal to the summation from I is equal to 1 up to n, v sub I squared times a sub I. So I'm going to take the velocity in area 1, square it, multiply it by the area in 1. And after I've done that summation, I'm going to get the total area by adding up all the areas. And I'm also going to get the average velocity by taking the 3 velocities and averaging those, squaring the average. And then when I go ahead and divide that through, now I have beta. So when I apply the momentum equation to my open channel flow, I'm going to use beta in my equation. And when I use the energy equation, I'm also going to calculate alpha, my energy correction coefficient. And that now is the same thing. That is the sum from J is equal to 1 up to M of V sub J cubed times A sub J. The whole thing divided by A sub T represents the total area times then the average velocity cubed. And this is very important. This is the one time in practice when we do use the momentum correction coefficient and the energy correction coefficient. So I think this is pretty straightforward. So I wasn't planning on doing an example because wherever you have a break right here, that's where you separate your channel. So the area in there is pretty easy to calculate. Either it's a rectangle or it's a rectangle with a little triangle. And down here, you can break this up into rectangles and triangles and find the area. And likewise here. And you have to know something about the velocity. The velocity is usually either given, someone went out and measured it, or you've used an equation to calculate it, like the Manning's equation. Okay, and then using those, we can calculate these 2 correction factors. And then when we apply them to our equations inside the program, then it gives us a better estimate of what's going on in that river. Okay? So for your homework problem, you're going to have an opportunity to calculate those for a compound channel. It shouldn't be too terribly difficult, right? All right. So with that, that finishes up chapter 3. And now we're going to move into chapter 4, which deals with pipe flow, which you've also seen briefly in fluids. Paper. We'll use the backs for today. Someone tell me in words, not necessarily equation, or you can tell me equation Y. What's the difference in between the Bernoulli equation and the energy equation? Remember that? Okay, great. That is correct. One of them has more stuff. I like that. So, Bernoulli equation. And this is not what we write. Bernoulli equation. P over gamma plus Z, well, P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G is equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G. Those online, can you see that okay? Okay, thank you. All right, so Bernoulli equation makes the assumption that the flow is 1D steady, incompressible, not incompressible, incompressible, and inviscid. Okay, inviscid meaning that we have no viscosity. All right. So when we get rid of this inviscid one, we're going to knock that out, and that's going to add more stuff to our equation. Now there are more ways of writing this equation than just this. This is the most common that civil engineers like to use. So if we go to the full energy equation, we have P sub 1 over gamma plus Z sub 1 plus V sub 1 squared over 2G plus or minus H sub M is equal to P sub 2 over gamma plus Z sub 2 plus V sub 2 squared over 2G plus then the head loss. And let's go ahead and break this whole thing down now, okay? So P sub 1, we've already called this before. This is the pressure head. And Z sub 1 is the elevation head. And V sub 1 is the velocity head. Okay. Once again, in hydraulics, head means length, so feet or meters. So the units then collapse to, I should say dimensionally it's a length, so units are feet and meters, so it collapses to feet or meters on any one of those terms. H sub M, that's mechanical. Okay, this is mechanical. And it is plus for a pump and minus for a turbine. It's mechanical energy, it's or shaft energy. So if we're adding energy to our system through a pump, we're turning a shaft or we're turning a piston, pushing a piston. So mechanical then adding energy to our system via pump or taking energy out of our system via turbine, okay? And we're going to keep it that simple, all right? Now, if I combine the pressure head and the elevation head, then I get what's called the piezometric head. And piezometric head is kind of an analogy to potential energy, if you will. It's not entirely true because pressure head actually does work, but we can look at it like potential energy. And we talked a little bit about that. A tank where the water's not moving, anywhere in that column of water, it has the same piezometric head, as long as it's a single fluid, all right? So now we've defined point 1 and 2 represent 2 points in our one-dimensional system. So the energy equation has the same thing up here, except for we get rid of that inviscid, which means now we can have viscosity in our fluid. Okay? We've got one last term on the energy equation that we need to describe, and that is H sub L, head loss. So like this is head loss. And head loss can be broken into 2 parts. So head loss is equal to H sub F plus H sub minor. So this is friction losses. And this is what we call minor or local losses. Okay. Now, minor losses is the most commonly used term, and it's also the most inaccurate term, because minor indicates that it's small, we really don't care about it. And for a lot of civil projects, like water system in a big city, that's true. But if you're dealing with a water system in a chemical plant, that's not true. It can become the major loss. How are we doing with time?
1 minute.
Oh, 1 minute left. Okay. So, so that's why I prefer the local term better, because it means that it's tied to a specific thing in our system, whether it's a valve or it's a connection, and we'll talk more about those on Wednesday. But I'm probably going to say minor, because that's what's commonly used. All right, but local is a better, accurate description of what those actually are. So on Wednesday, we're going to start going into the energy equation, and we're going to be on the energy equation for several weeks. We're going to look at it and apply it to a lot of different ways. So probably by Wednesday is when we will cover everything that you have covered in fluids, and we'll start getting into some new stuff. I know we've hit some relatively new things like the energy correction coefficient and so forth, but now we're really ready to move forward and dive right in. So have a great day, and I'll see you on Wednesday.
Yes. IPO wants to fill up this form for the CPQ.
Oh, yeah. ITD or IPO?
It's for IPO.
Yeah, IPO. Hold on a second. Let me get this going here.